Good day everyone! In this video, we will be doing an exciting experiment wherein we will detect and measure the pH level of different household materials. In this experiment, we will be using a natural pH indicator which is more affordable yet effective. Acids and bases play an important role in chemistry and also in our everyday lives. We experience these two factors every day, from drinking a very sour lemonade, a hot espresso, washing our hands with soap, and cleaning with bleach. Within the laboratories, scientists classify various acids, bases, or neutral substances and determine their pH levels through tasting, smelling, or by using a pH indicator. Acids and bases are two categories of corrosive substances. Any compound or substance that has a pH value between 0 to 7 is considered acidic, whereas any compound or substance that has a value that ranges from 7 to 14 is considered as base. The pH level 7 is considered as neither acid or base, hence, it is known as neutral. An acid is any molecule or substance that has a pH value of less than 7 when it is present in an aqueous solution. We all know that an aqueous solution is any solution wherein water is used as a solvent. It is called a proton donor or compound that donates hydrogen ion to another compound known as base. The strength of acid depends on the concentrations of the hydronium ions. A base, or alkaline on the other hand, is any molecule or substance that has a pH value of greater than 7 and even reaches 14 when they are very strong. They are known as proton acceptors from another compound known as acid. The strength of base depends on the concentration of the hydroxide ions. When acids are dissolved in water, they are sour in taste, they are sticky, they react with active metals to liberate hydrogen, react with bases for neutralization of their properties, and release hydrogen ions. Examples of commonly found acids are batteries, edible foods such as lemon, tomato, vinegar which are sour in taste, coffee, and milk. When bases are dissolved in water, they are bitter in taste, slippery to touch, react with acids for neutralization of their properties, and release hydroxide ions. Examples of commonly found bases are soap, baking soda, blood, bleach, and stomach tablets.
Hi, I am Annika. Now I will classify the three concepts that involve acids and bases. These are the Arrhenius concept, Bronsted-Lowry concept, and the Lewis concept. First, the Arrhenius concept. The Arrhenius acid-base theory was proposed by Swedish Svante Arrhenius and is considered the first ever modern approach to the acid-base concept. According to this theory, acids are the compound that increases the concentration of hydrogen ions or protons in an aqueous solution. A base is a compound that increases the concentration of hydroxide ions when dissolved in water. The released hydrogen ion or proton then exists in a combined state with the water molecule and forms hydronium ion. Common examples of Arrhenius acid involves HCl or hydrochloric acid, H2SO4 or sulfuric acid, and HNO3 or nitric acid. Next, we have the Bronsted-Lowry concept. The Bronsted-Lowry theory is somewhat a more general acid-base theory. This theory is proposed by a Danish chemist named Johannes Nicolaus Bronsted and English chemist Thomas Martin Lowry. This theory respectively defines an acid as a proton donor and a base as a proton acceptor. In this theory, the reaction of an acid and base is represented as an equilibrium reaction. The advantage of this theory is its predictive capacity. It can foresee whether the equilibrium lies towards the reactants called reactant favored or towards the product called product favored. These events are determined by the relative strengths of the acids and bases. And last but not the least, the Lewis concept. In 1923, chemists Gilbert and Lewis suggested another way of looking at the reaction between hydrogen and hydroxide ions. In the Lewis theory of acid-base reactions, bases donate pairs of electrons, whereas acids accept pairs of electrons. Therefore, a Lewis acid is any substance such as the hydrogen ion can accept a pair of non-bonding electrons. Through the use of Lewis' concept of acids and bases, scientists and chemists are now able to predict a wider variety of acid-base reactions. Moreover, pH indicators have a significant purpose. The importance of pH indicators is that they determine whether the substance is an acidic or a basic substance. When indicators are put to an acidic or basic solution, they change color. And the colors change differently for acids and bases. As a result, the indicator can help us determine whether a solution is considered acidic or basic. In addition, acid-base indicators are substances that react to hydrogen ion concentration variations. They are generally weak acids and are also known as pH indicators. Furthermore, indicators are used to assess whether a solution is basic or acidic by utilizing a color shift and a pH range. Lastly, the chemical conditions of a solution are also reflected by pH, which is an essential quantity. Thus, pH indicators are highly significant and are used to monitor safe water conditions.
The materials needed in conducting the experiment, we have 2 eggplants, water, clear plastic cups, heat-resistant container, dropper, white paper, 10 ml syringe with no needle, baking soda, tomato juice, vinegar, and calamansi. Let's proceed to the experiment. For the preparation of natural pH indicator, after we peel 2 eggplants, we allow the peels to air dry for 2 days away from direct sunlight. By utilizing a heat-resistant container, we boiled 250 ml of water and soaked the dried eggplant peels in the hot water, and waited 5 minutes and until most of the peels have turned a yellowish-green color. After waiting, we remove the peels and allow the remaining solution to cool before we use it. And now, we are in the part of the testing of pH. In a separate plastic cup with labels, and those are baking soda and tomato, by using a dropper, we added 10 drops of tomato juice in the tomato cup. By using a teaspoon, we added 1/2 teaspoon of baking soda in its cup. By using a syringe with no needle, we added 5 ml of water in each cup of baking soda and tomato. By using a syringe with no needle again, we added 10 ml of the natural pH indicator in each cup of baking soda and tomato. And mix it thoroughly. And we observed for the color change. We added more indicator to observe a stronger color change. As a result of our experiment, the color of the baking soda is fern green and corn yellow for tomato. These two pictures are the result of our experiment for baking soda and tomato. The left cup is without pH indicator, and on the right cup is with pH indicator. By utilizing a heat-resistant container, we boiled 250 ml of water and soaked the dried eggplant peels in the hot water and waited 5 minutes and until most of the peels have turned a yellowish green color. After waiting, we remove the peels and allow the remaining solution to cool before we use it. In a separate plastic cup with labels, and those are vinegar, calamansi, and water. By using a tablespoon, we added 2 tablespoons of vinegar in vinegar cup. By using a syringe with no needle, we added 5 drops of calamansi in its cup. And we added 1 teaspoon of water in its cup by using a teaspoon. By using a syringe with no needle again, we added 10 ml of the natural pH indicator in each cup of vinegar, calamansi, and water. And we mix it thoroughly and observe for the color change. As a result of our experiment, the color of the vinegar is light yellow and calamansi is orange and dark green for water.
For our results and discussion portion, we will be answering questions regarding the experiment we have just conducted. Number 1. What color was the indicator for acidic solutions? What about basic and neutral solutions? What was the order of your samples from most acidic to least acidic? The color of the indicator varies from different substances used in this experiment. The anthocyanin indicator turns red-pink in acidic solutions, reddish-purple in neutral solutions, and green to blue for basic or alkaline solutions. Due to the fact that only one natural pH indicator is used, the indicator is yellowish in acidic solutions and also yellowish in basic and neutral solutions. Now, to determine the order of our samples, we refer to this image. Thus, from most acidic to least acidic, we have calamansi, which is color orange, will fall in number 2. Vinegar, which is light yellow, will fall in number 3. Tomato, which is corn yellow, will fall in number 4. Water, which is dark green, will fall in number 7, and that is neutral in our pH scale. Baking soda, which is fern green, will fall in number 8, and that is the basic or alkaline solution in our experiment. From most acidic to least acidic, calamansi is orange for number 2, vinegar, light yellow, number 3, tomato corn, yellow number 4, water, dark green, number 7, and baking soda, fern green, which is number 8. Now for our second question, what is the organic compound responsible for the color changes observed? What is the basis for these color changes? To answer that question, the acid-base indicator was the organic compound responsible for the color changes observed. Acid-base indicators are organic compounds that change in color in aqueous solutions, signifying whether the solution is acidic or basic. In addition, the basis for these color changes is the dissociation of hydrogen ion from the indicator, causing a pH indicator's color to shift. Furthermore, pH indicators include both natural colors and weak acids. The weak acid indicator dissociates, causing the solution to change color. Question number 3. Red cabbage is the usual plant source for this kind of experiment. Why do you think it still worked even though we used eggplants? In this experiment, we used eggplant peels to detect the pH level of the used substances. But in fact, red cabbage is the commonly used plant source for this kind of experiment. To explain, we all know that red cabbage, although technically not red, and the eggplants are color purple or in violet in nature. The reason why, even though the plant source used is different, both the red cabbage and the eggplant have the same pigment-creating component called anthocyanins, a phenolic compound, which explains why it has the same effect as the red cabbage. The most common anthocyanin that is most often linked to the purple color of aubergine is nasonin, which came from the Japanese word for aubergines, nasubi. Fun fact, this pigment-creating component, anthocyanins, also gives the eggplant its bitter taste. By air drying the peelings of the eggplant for 2 days and soaking it in water, the anthocyanin molecules will dissolve into the water as well.